subprograms. We saw there's about 50 different names for them. Subroutines, functions, subprograms, modules, all sorts of different things. They do that, I think, to try to keep the pay high, but it's not that different than most job functions where we have some different ways of looking at things. So the last thing in our content talking about subprograms is recursion. And recursion is important, and I've actually seen some of you do it in some of your Python code, so it's really important for us to be aware of recursion and what it is. And a recursive subprogram is simply a subprogram that calls itself. So they have this little formula written down here to show us kind of an algorithm that we could use to demonstrate recursion. So let's write this code in Python. Let's put it straight in our Python tutor website so we can watch it run. pythontutor.com. And I'm going to do the start visualizing your code now, and I'm going to use Python 3.6. This recursive function is really quick. It does not have a lot of code, so it's just take us a second. In our recursive function, I will put a comment here. Recursive function, we won't do a lot of commenting since we're using our Python tutor site. You're going to write some code, Micah. Get on Python tutor site with us. So it says, looking at the pseudocode, this algorithm is pretty simple. We're going to create this function named sum that expects a parameter of a number that's going to be called n. And in our function, we're going to check to see if n is 1. If it is, we'll return the value of 1. Remember, in our pseudocode, they do that return by setting the name of the function equal to some value, and that's the return. Now, if n is not 1, it's some other number, I'm going to use n minus 1 to call sum again. So that's my recursive call, where this function is calling itself within the function. So let's write that function in Python. We'll do our def statement, and we're going to call that function sum, just like they did, and say that it's going to expect a parameter named n. So that's all we need to do to declare that function in our Python code. Let's have our def statement for it. Now, inside our function, just like they have in the pseudocode, we'll do an if statement at the very beginning, and we'll check to see if n is 1. And if it is, we'll just return that value of 1. If it's not, we're going to do this recursive call. They say they've got it here in several different formats, but we'll basically be saying we want a variable named sum. Oh, I don't need that yet. Hang on. Look at my cheaty code. If our n value passed to us is 1, we'll just return a value of 1. We'll return that value. But if it's not, we'll call our sum function again, passing in the value of n minus 1. When the sum function returns the value to us then of its processing, we'll add n to that value before we return it. So this is kind of a fun and games thing. Now, when we call our sum function, we're going to call it in a print statement. And we saw last time that if we call a function within a print statement, we'll get the results of the function printed. So let's let everybody get that code in. So in our print statement, we're just calling our recursive function, and the first time in, we're going to pass a value of 5. Now we're going to run this thing, and then we'll look at our little worksheet and kind of try to use our thought processes to analyze it. So everybody got the code in? Let's try running it. Now, when I visualize execution on this, I'm going to start out, again, reading all of the code, and the visualizer will note, oh, there's this function called sum, and it expects this parameter named n to be passed to it. Now, in our main line on column 1, we're going to use our print statement to call that sum function, passing a value of 5. So here we go. Our sum function is set up in memory, and as it started, the system says, here's your value of n, it is 5. That's what was passed to you, so you're ready to get started. So in our sum function, the first thing we do is check to see if the value we were passed is 1. It's not, so we'll perform our else statement. Now in our else statement, the first thing we're going to do is subtract 1 from n to give us a value of 4 and call our sum function again. So let's see that. Here it is. So now our sum function is active in memory 2 times, right? But this one that's gray is the one that's executing, and it has a value of 4 for n. Now, as we start executing our sum function with that value of 4, we see it's not equal to 1, so we're going to perform the else processing again. This time, n is 4, so we'll subtract 1 from it, making it 3, and call sum again with a value of 3. So now, if you notice, sum is executing in our memory 3 times. As it begins, it checks to see if n is 1. It's not, so it performs its else clause, making the value passed to our new execution of sum 2. Now, that execution of sum starts running, and n is not 1, so it's going to call itself again, this time, finally, passing a value of 1. So notice over here, looking at your visualizer, the sum function is running now 5 different times. We're concerned about this last time right now, where the value of n was 1. As I execute our sum function with that value of 1, our if statement's true now, so this sum function is going to return the value of 1 to the prior sum function. So let's do next, and we'll see that value of 1 gets returned to our prior sum function. Now, that sum function is sitting here on this line of code, and it just got this value of 3 returned from calling the sum function. So now it's going to add its value of n, which is 2, to do its own return to the prior version of the sum function. So we'll be returning a value of 5. Oops, sorry, 6. I said that wrong. Now, this is our sum function that was called with n equals 3. So when it gets this return value of 6, It's going to add that original 3 to it and do its own return to the prior execution. So our return value out of this one should be 9, if I can add correctly, and I can't, so it is 10. Now, our value of n is 4 here, so we'll end this execution of our sum function by adding those together and returning to our original execution of the sum function. We're going to do this on a piece of paper here so that we can really visualize it. Now, I want to start running this thing again so that we can look at it on our worksheet. I don't know what else to call it. It's not really a worksheet. So let's write this down ourselves. The first time we look at our sum function, let me get a copy of it myself so I can show it on my camera. Yeah, that would be the best way. When you look at these recursive functions, it's really hard to see what's going on. Hard enough to look at functions themselves. But when a function calls itself, it gets kind of deeply involved. So let's see if I can get on here. I'll do some super fancy old school stuff. So here's my sheet.
I'm surprised you're even allowed to.
I know, can you do it? Can you imagine? Yes, sir.
Do you have an extra copy?
It's right behind you. Did you get one of these too? Grab one. Anybody else that needs one, just grab one there. Yeah, I didn't think I would get it to connect, but it connected. All right, so let's try this. Yeah, I've got like this really high-tech, low-tech thing going. All right, so I'm going to start at the very first. I'm going to call sum for the first time. I'm going to put a number 1 down here. I don't know if that is perfectly clear, but it's our first execution of sum. Now, for this first execution of sum, n is 5. So I'm going to put that there on my sheet, n is 5. N minus 1 then would be 4. So now I'm going to use that number 4 to call sum again. Let me execute this code online so that we can kind of think about it. So here, the second execution of sum is going to start with this number 4, right? And its n minus 1 value would be 3. Now, as we execute through, we'll see that because n is not 1, we're going to call sum again using that value of 3. So our third execution of our sum function is going to have an n value of 3. So n minus 1 would be 2. As we execute our function, that does not give us a value of 1 yet, so we'll call our sum function again. This will be the 4th time we've called the sum function, and this time we'll be calling it with that value of 2. Now, 2 minus 1 is 1, so I've got that down here. But as we execute our sum function for the value of 2, it's not 1 yet, so we'll call our sum function one more time. That's our 5th execution of the sum function, and it's starting with the value of 1. Now, as we execute our sum function with that value of 1, our if statement is true. So we never calculate n minus 1, we just return a value of 1. So I'm going to put this return value over here. That's the value I'm going to return from this 5th execution. Now, when I execute that return, my 5th execution disappears, goes away, But my fourth execution sees that number 1 sitting there as that return value. Now, it's got to execute the addition. Whenever we return what's left over in our code from this part that said sum n minus 1 is that return value. So here for my fourth execution of sum, my return value is 1. My original value of n is 2. So the value I'm going to return is 1 plus 2, or 3. So I'm going to return that value up to the one above. Now, for that third execution that got that return value of 3, it's now ready because it's got its return value. And it can say, oh, I need to take that return value and add it to my value of n, which was 3. So that means the return value I'm going to have is 6. All right, so I'm going to put that 6 up there above, because as I finish executing my sum function for that third time, I return that value of 6. Now my second call to my sum function gets to take back over processing. And so it says, oh, I got this return value of 6. I'm going to add n to it, which was 4, and I'm going to return a value of 10. So finally, I'm back to my first call of the sum function, and it takes that value of 10 and adds n to it, which is 5, and gives us a final answer of 15. So we finally print that out. So I don't know if looking at it that way with our worksheet makes it better or worse. But for me, it somehow helps me be able to visualize the fact that I have all of these different versions of this sum function running, and each one is not finishing this calculation until it gets a return value supplied. So it's kind of like a bunch of dominoes that are going to fall down, that are going to crash. The one before it has to go down before this one can go down. Better, worse, no different? Tell me. See if I can find my Teams function and stop that. Okay, I think I stopped. Double check here. All right, questions about that?
The proper definition of the return function?
What is what?
Like the return function's actual, is it just to send it back to the beginning of the loop?
Right. Well, just to send it back from the function. So the function's ending, and it's like passing off the baton to the person that called it. So that's, you can kind of think of it as a relay race. Our main function is running, it's got the baton, it calls a function, passing that information to it. That function takes over and does some stuff, and then it may pass on some additional information or return information back to that main caller. So when we're working with our functions, we're thinking about doing some sort of almost hidden processing that we don't want anybody else to worry about, but we have to be telling them, I need these things, these pieces of data to be able to do this function for you, and then we return the value to them after we've done that processing. So recursive function is just one that calls itself. Now let's save this code. I'm going to go back to edit this code. So get it entered, and if you don't have it on Python Tutor, enter it directly into Replit to save it. I want to copy that, and then I'm just going to go to Replit and create a new Replit to save it in. So here I'll do a new Python, and I'll make this one L11. recursive function. Now, the definition of a recursive function is really easy. You can always remember it. It's a function that calls itself. But you guys see when we look at that code that actually understanding what's going on in that execution can take a little bit more of a thought process. So we've got that there. I'll add some more comments. Got it from our book pretty much. So we were able to take that pseudocode, that algorithm, and pretty directly convert it into Python code. Remember, that's not always the case. Depending on the logic and stuff, it might be something that's harder for us to implement in Python, or it might be easier. But either way, as long as we've got that algorithm documented in Python code or pseudocode or something, we can refer to it later. So this is demo, a function that calls itself. Now I know you guys have different ways of gaining an understanding about things. All Gen Zers that have just like computers in your brains, right? But there are some things you can do to help understand some things. I don't have that kind of Gen Z computer in my brain. I'm kidding you guys. But I can go online, and so I searched for GIFs, because I was wanting to find something that's sort of animated. Because for me, visualizing the process really helps me to understand what's going on. Different people are different. Some of you can gain an understanding without that visualization. Some people need a little bit more. But I searched for a call function GIF, and then I'm just looking at images. And this person here, I don't know if it's a teacher or what, but they have a bunch of different images that are like different GIFs and things that just show different function machines. And I think it's just this person's idea, of how to explain a function. I got that outer one, not the inner one. So there's all sorts of different pictures. Some of them are animated, some of them aren't. But you can just get kind of an idea of what's going on. Yesterday in one of the other classes, somebody said, oh, a function like a math function? Well, that's a really hard question to answer because, yeah, like a math function, exactly, that math function has to have input from you and it supplies the answer to you, right, from the function. But we're creating our own. So we have to decide, what do I need as input and what's my output going to be? This gumball machine demonstrates it. You could put your money as input and get your gumball as output. But anyways, there's lots and lots of different GIFs and things like that that you can use to kind of visualize things to help you get an understanding of it. Some of them are even just like actual code, where they show you some code and say, this is a great function. So that's all helpful, anything you can do. And one thing I want to say before I let you guys go off and work on your lab time is that we're in an intro class, right? It's intro to programming. So when we look at these concepts, we're developing an understanding, but it's still an introductory understanding. So to not have a deep, deep, deep understanding is okay because we're beginning to understand the concepts. You're going to work with these concepts again in different programming languages if you're in the CIS degree. So maybe in Java, in C#, you'll see how they implement functions and get some more opportunity to practice. So My point is it's okay to be where you are in your understanding level. You know, if you've got a really good grasp of it, great. Try to help other people get to that point. But if you don't, that's okay too, because we're just beginning to work with the concepts and getting to a point where we can develop an understanding of them. So that's all right. Now I wanted to show you this other program. Let me see if I can find it real quick. Because it is one that somebody created in a class. Oh, it's the 8-ball game. So this is a person that has more programming experience. And they used some things that we haven't done yet, but that's fine. In their program, they created a function for their magic 8-ball response. If you remember that one the first time through, because you're going to get a chance to do this in a couple of different ways, we just generated a random number and gave the user a response based on that. And that's exactly what this one is doing. So we don't have to worry too much about the code that they're doing, but they decided to make it into one where they ask the user if they want to play again, to add that play again loop. And to do that, they made their magic 8-ball function recursive, right? At the end, it calls itself again. So that means when I run it, here we go, this comes out of that function, this message. Press any key for answer and Q to quit. What is your name? Okay, so I'll put in my name. And then I get the same thing, but I'm getting my 8-ball answer here. So as long as I just keep pressing enter, putting in my name or my question or whatever, it'll keep giving me answers, which is fine. That's great. So we're getting this repeating thing by calling itself. So it's not in a while loop, it's calling itself. So that's the part I want you to notice. Don't worry about any of the other code, the way that they're doing things, stuff like that. Just the fact that this magic 8-ball function is calling itself. Now I'm going to take it to our Python tutor site because I want to show you how this runs when it's calling itself. So here I am, the very first time I'm going through, and I've got my setup here that I've got this global variable. That's my random number and an answer variable. And then I set up my magic 8-ball function. Now, the very first time through, we call our magic 8-ball. Here it starts up and it does some stuff, asks some things. I can pretty much input anything, and it gives us a response. Now, as it's going, it's kind of slow, sorry, as it's looking at all of these things. But I wanted you to notice that this guy uses a list. So every time it calls itself, it builds this list of all of the responses. That's nice. And then it picks one and it gives it, prints it out, and then it calls magic 8-ball again. So now we have magic 8-ball running in memory once. Here it is the second time. Now the second time that I was like, sure, I want to run it again, it's going to set up that whole list in memory again. My phone is doing weird things. I don't know what my phone is doing. I shouldn't have got on that Teams session. But now I've got magic 8-ball running twice, and it has this giant list of things out here twice. But now it's going to come up with an answer. spit it out, and then say, do you want to do this again? By calling itself again. So now here's our third time the magic 8 ball is in memory. I'll go ahead and say, sure, I want another answer. So it's going to build that big table again, list of entries, and send me an answer. And then it's going to run itself again to ask me if I want another one. I'm like, sure, yeah, I'd like to play this game all day. So now, again, it's going to build its big list in memory again. So what I want you to notice from this is this person didn't mean to make this magic 8 ball function a recursive function. They didn't mean to make it be in memory all these different times. They were just trying to make it have a looping ability. So we should use a while loop to do that kind of thing instead of using this recursion. Because notice how this recursive function is eating up all sorts of resources that are unnecessary. It should have just said, do you want to run again? Yes. Okay, I'm going to execute my same loop again. But instead, it's like, oh, I'm going to do this really cool trick, and I'm going to call my cells at the end of my cells so that I can see if they want to run again. Well, if somebody were using this function or playing this game for several hours, think about how many times I could have this magic 8 ball function in memory. Each time it's in memory, it's got this whole list of possible answers that it's building. So each time I say, sure, I want to run it again, it's using more resources. So recursion is something for us to be very aware of, because this process would eventually eat up all of the available resources on a machine, right? And just take it down, because we've now recursived ourselves into a place where we're using so many resources that the system can't continue functioning. Now, if I finally say Q, I'll Q here. The way that this thing is set up, it will end each of the different instances. Let's let it build it. There it goes. And finally, it looks at my Q and gets rid of that one. And I have to keep putting in the Q, because every time this 8 ball thing called itself, I have to respond again to tell it to quit that execution of it. And so it's kind of a buggy sort of thing. So I just wanted to show you that to show how easy it is as a beginning programmer to get into some sort of idea that looks really cool, but if we're not looking at how it's utilizing resources, it could be a problem. So recursive functions are great when they're working, like in the number that we were looking at, that calculation, but not so great by accident. So just know how you guys can use these tools to make sure that you don't have something like that happening. Now, in the end, this sum function, if you saw, what it did was it starts with a specific number like 5, and it added 5 plus 4 plus 3 plus 2 plus 1. So it did like a combination. So that was what its processing requirements were as it started out, and it decided to do it in a recursive function. All right.